The cosmic horizon, what lies beyond the observable universe. There are places in the universe you can never visit, never see, never know. Not because they're too far away, not because we lack the technology, but because the fabric of space itself is expanding faster than light can travel through it. Right now, at this very moment, galaxies are crossing an invisible boundary. Once they pass this threshold, they vanish from our universe forever. No amount of technological advancement will ever bring them back. They're not just unreachable, they're unknowable. The observable universe has an edge, a horizon beyond which reality becomes fundamentally inaccessible to us. And that horizon is shrinking. Every second, we lose approximately 20,000 stars, gone. Not destroyed, simply pushed beyond the cosmic horizon, where light from them can never reach Earth again. What if I told you that everything we can observe, every galaxy, every star, every planet, represents less than 3% of the actual universe? What if the cosmos extends far beyond what physics permits us to see? Today, we journey through evidence that challenges everything we understand about the scope of reality itself. Prepare yourselves. We begin. Act 1. The Discovery. In 1929, astronomer Edwin Hubble made a discovery that would shatter humanity's understanding of the cosmos. Working at the Mount Wilson Observatory in California, Hubble noticed something extraordinary in the light from distant galaxies. They were all moving away from us. Not just moving, fleeing. The farther away a galaxy was, the faster it receded. Hubble had discovered that the universe itself was expanding, carrying galaxies apart like dots on an inflating balloon. But Hubble couldn't have known the full implications of his discovery. He couldn't have imagined that this expansion would create an invisible boundary around us, a cosmic horizon beyond which reality becomes permanently inaccessible to us. To understand this horizon, we need to grasp a fundamental truth about our universe. Space itself can expand faster than the speed of light. Einstein's theory of relativity prohibits objects from moving through space faster than light. But the expansion of space itself follows different rules. Space can stretch at any rate, and in the far reaches of the cosmos, that expansion exceeds light speed. Picture yourself on an enormous treadmill that's accelerating. You're running forward at your maximum speed, analogous to light traveling through space. But if the treadmill speeds up faster than you can run, you'll actually move backward relative to the room around you. You're running forward with all your might, and yet you're losing ground. This is the cosmic horizon. In the 1990s, two independent teams of astronomers made a discovery that would earn them the Nobel Prize and fundamentally change our understanding of the universe's fate. They were studying Type 1a supernovae, stellar explosions that serve as cosmic measuring sticks because they always release the same amount of energy. What they found defied all predictions. The universe wasn't just expanding, it was accelerating. Something was pushing galaxies apart faster and faster. Scientists called this mysterious force dark energy, though the name reveals more about our ignorance than our understanding. Dark energy makes up approximately 68% of all energy in the universe, yet we have no idea what it is. But we know what it does. Dark energy ensures that the cosmic horizon will not merely exist, it will close in around us. The observable universe is shrinking. Saul Perlmutter, leader of one of the discovery teams, put it simply: we're living in a universe where isolation is built into the very fabric of space-time. The horizon currently sits approximately 46.5 billion light-years away. Yes, you heard that correctly, 46.5 billion light-years, even though the universe is only 13.8 billion years old. The expansion of space itself has stretched that boundary far beyond where simple multiplication would suggest. But here's where the concept becomes deeply unsettling. Light from the most distant observable galaxies has been traveling toward us for over 13 billion years. When that light began its journey, those galaxies were perhaps 36 billion light-years away. But during the light's journey, space expanded. Those same galaxies are now over 46 billion light-years distant, receding from us roughly 3 times the speed of light. We're seeing the ancient past of objects that are now fundamentally unreachable. We picture for galaxies and planets across our observable universe a ghost of memories, of objects that have already crossed beyond the horizon of causality. We exist in separate universes now, divided not by distance, but by the expansion of space itself. Astronomer Mario Livio describes it as cosmic solitary confinement. We're sealed inside an expanding bubble, watching the walls close in. The implications cascade outward like ripples in dark water. If there are civilizations in galaxies beyond our cosmic horizon, we cannot communicate with them. We cannot detect them. We cannot prove they exist. Any signal they send towards us will never arrive. The expanding space between us will stretch their transmissions until the wavelengths become infinite, the energy approaches zero, and the message dissolves into the quantum foam of reality itself. They could be asking the same questions we are, staring into their skies, wondering if anyone else exists in the vast darkness. They could be signaling, broadcasting, calling out across the void. We will never know. The cosmic horizon doesn't just limit our sight, it limits causality itself. Events beyond the horizon cannot affect us. Information cannot reach us. The universe beyond might as well not exist, at least not in any sense that matters to physics or philosophy. But the evidence forces us to confront an uncomfortable possibility. What if the universe beyond our horizon is not just larger, but fundamentally different? The mathematics of cosmic inflation, the theory that explains how the universe expanded exponentially in its first fractions of a second, suggests something profound. Our observable universe likely represents an infinitesimal patch of a vastly larger cosmos. How much larger? Some calculations suggest the full universe is at least 10 to the 23 times bigger than what we can observe. That's 10 billion trillion times larger. Other models suggest it might be infinite. If true, the cosmic horizon doesn't just hide more of the same. It conceals realms where the fundamental constants of physics might differ, where the laws of nature could take different forms, where reality itself might operate according to rules we cannot imagine. We stand at the shore of an infinite ocean, able to see only the water immediately around us, unable to know what lies beyond the fog at the edge of perception. The evidence suggests we are surrounded by forever, and we are utterly alone inside our shrinking bubble of observability. Act 2, Part A, Observable Signatures. Scientists discovered the first concrete evidence for the cosmic horizon through an elegant piece of observational astronomy. In 2004, the Wilkinson Microwave Anomaly Probe mapped the cosmic microwave background, the afterglow of the Big Bang, with unprecedented precision. This ancient light, released 380,000 years after the universe's birth, reveals patterns that encode information about the structure of the cosmos. The patterns show sound waves that rippled through the early universe, compression waves in the plasma that filled all of space. Physicists can calculate the largest possible sound wave that could have formed by the time the cosmic microwave background was released. That wave left an imprint, a characteristic scale in the patterns we observe today.
This sound horizon measures approximately 456,000 light-years across. By comparing that scale to how large those patterns appear in our telescopes, scientists can calculate exactly how far away that ancient light source is. The answer? 46.5 billion light-years, accounting for expansion. This number defines the cosmic horizon with mathematical precision. But scientists discovered something even more revealing in the data. The cosmic microwave background contains patterns at every observable scale except beyond a certain size. Above approximately 10 degrees across the sky, the patterns become statistically uniform. They contain no information. This cutoff exists because we're observing the edge of causality itself. Regions of space separated by more than this distance
at the time of the Big Bang could never have influenced each other. They exist beyond each other's horizons. The uniformity we observe is not because those regions are inherently similar, but because they never communicated, never coordinated, never even knew the other existed. The cosmic microwave background is showing us the scars of isolation built into spacetime's architecture. Scientists discovered additional evidence in the distribution of galaxies themselves. The Sloan Digital Sky Survey, which mapped over 200 million astronomical objects, revealed that galaxies form a cosmic web, vast filaments and sheets surrounding enormous voids. But the size of the largest structures tells us something profound. The biggest known structure in the observable universe is the Hercules Corona Borealis Great Wall, a filament of galaxies stretching 10 billion light-years across. This structure formed from tiny quantum fluctuations in the early universe that grew over billions of years through gravitational collapse. Here's what matters. Structures this large required nearly the entire age of the universe to form. We're observing structures that formed at the absolute limit of what's possible given the time available since the Big Bang. The universe is showing us its age through the size of its largest features. And those features tell us something else. If the universe beyond our horizon is significantly different, if the laws of physics vary, or if the density of matter differs substantially, then structures at the horizon should appear distorted or anomalous. They don't. This suggests that the universe remains relatively uniform, at least somewhat beyond what we can observe. The cosmos doesn't end at our horizon. It continues, following the same basic rules, at least for some distance into the unknowable. But this represents just one piece of a much larger puzzle hidden in the mathematics of cosmology. Physicists working with the equations of general relativity discovered that cosmic horizons aren't unique to our expanding universe. They're a fundamental feature of space-time itself, appearing wherever acceleration exists. If you accelerate through space in a rocket, you create a horizon behind you, a region from which light can no longer catch up to you. This is called a Rindler horizon, and it's mathematically identical to the event horizon of a black hole. The cosmic horizon is the same phenomenon, but created by the acceleration of space's expansion rather than the acceleration of a spacecraft. This mathematical equivalence reveals something profound. Horizons are not aberrations, but fundamental features of relativistic spacetime. They emerge naturally whenever acceleration exists, and our universe's accelerating expansion ensures that the cosmic horizon is not just real, it's permanent. Part B. Deeper implications. The most remarkable discovery involves what happens to objects as they approach the cosmic horizon. In 2015, physicist Lawrence Krauss calculated exactly what an observer would see if they could somehow watch a galaxy cross the horizon boundary. The results are haunting.
As the galaxy approaches the horizon, its light becomes increasingly redshifted, stretched toward longer wavelengths. Red visible light shifts to infrared, then to microwaves, then to radio waves. The light doesn't disappear, it fades from view as its wavelength becomes too long to detect and its energy drops towards zero. But from the galaxy's perspective, nothing special happens. There's no wall, no barrier, no discontinuity. The galaxy continues existing, its stars shining, its planets orbiting. The horizon is entirely one-sided, real for us, but imperceptible to those beyond it. This asymmetry reveals something disturbing about the nature of reality. The cosmic horizon divides space-time into regions that exist for some observers but not others. Your observable universe and mine overlap but are not identical. Every point in space has its own unique cosmic horizon. Reality is observer-dependent at the largest scales. Scientists studying the mathematics of cosmic horizons discovered an even stranger implication. Physicists Stephen Hawking and Jacob Bekenstein proved that horizons contain entropy, a measure of information or hidden states. The horizon around a black hole contains entropy proportional to its surface area. This fact leads to the holographic principle, which suggests that all information about the volume of space is encoded on its boundary. The cosmic horizon follows the same rules. This means the observable universe's total information content is determined by the surface area of the cosmic horizon, not by its volume. Everything we can ever observe, every particle and field and quantum state within our 46.5 billion light-year sphere is fundamentally encoded on a distant two-dimensional surface. We might be living inside a hologram. The implications extend further. If information is preserved at the cosmic horizon, then in principle, everything that crosses the horizon leaves an imprint, a shadow, a trace encoded in the microscopic structure of space-time itself. The universe might be keeping records of everything it loses. Recent observations reveal patterns that shouldn't exist under conventional cosmology. In 2007, astronomers discovered the cold spot in the cosmic microwave background, a region approximately 1.8 billion light-years across that appears slightly cooler than surrounding areas. The cold spot shouldn't exist. Statistical analysis shows that a deviation this large has less than 1% probability of occurring by chance. Various explanations have been proposed. A supervoid between us and the surface of the cosmic microwave background, a cosmic texture left over from the early universe, or even a window into a parallel universe that collided with ours billions of years ago. But another possibility emerges from horizon physics. If our observable universe represents a bounded region with specific boundary conditions imposed by the cosmic horizon, then we should expect subtle anomalies at the largest scales, places where the constraints of the horizon create patterns in the observable cosmos. The cold spot might be one such signature, a fingerprint of the horizon's influence on the structure of space-time itself. The evidence extends beyond the cosmic horizon into the realm of quantum mechanics. In quantum field theory, empty space isn't empty. It seethes with virtual particles, quantum fluctuations that pop into existence and annihilate within timeframes shorter than any measurement can detect. Near horizons, something remarkable happens. A horizon splits virtual particle pairs. One particle falls beyond the horizon, while its partner remains observable. The horizon turns virtual particles into real ones, extracting energy from the gravitational field in the process. This is Hawking radiation, typically discussed in the context of black holes, but the cosmic horizon exhibits the same phenomenon. Our cosmic horizon glows with an infinitesimal temperature, approximately 10 to the minus 30 Kelvin. This is far too cold to ever detect, buried beneath the 2.7 Kelvin cosmic microwave background. But it's real. The horizon radiates. This radiation means the cosmic horizon is not passive. It actively affects the quantum vacuum, altering the properties of space itself at right the edge of observability. We live inside a cavity whose walls are quantum mechanically active. Act 3. The Big Picture. Part A. Theoretical Framework. The theory that ties everything together is eternal inflation, developed by physicists Alan Guth, André Linde, and others starting in the early 1980s. Eternal inflation proposes that the Big Bang wasn't a single event, but an ongoing process. Space inflates exponentially in most regions, but occasionally decays into slower expanding bubbles. Our observable universe is one such bubble. The theory makes a stunning prediction. The cosmos contains infinite bubble universes, each with its own cosmic horizon, eternally separating them from one another. The space between bubbles continues inflating forever, ensuring they never collide or communicate after formation. This framework explains why our observable universe appears homogeneous. We're observing a single bubble that underwent a brief period of rapid expansion, smoothing out irregularities. But beyond our horizon, the cosmos continues its eternal dance of expansion and bubble formation. Alan Guth describes it as
a universe that reproduces itself, creating copies that are forever isolated from one another. Leading physicists remain divided on what this means for the nature of reality. André Linde, professor at Stanford University, argues that eternal inflation is not just likely, but inevitable, given our understanding of quantum field theory. Once inflation starts, Linde explains, it never completely stops. Quantum fluctuations ensure that some regions keep inflating forever. But eternal inflation forces us to reconsider fundamental assumptions about existence itself. If the process creates infinite bubbles, and if quantum mechanics ensures variations in the initial conditions, then every possible configuration of matter and energy must occur somewhere. Not just once, but infinite times. This implies infinite copies of you exist beyond the horizon. Not similar people, exact duplicates, living identical lives, thinking identical thoughts. The mathematics is unambiguous. In an infinite universe with finite possible quantum states, repetition is inevitable. Physicist Max Tegmark calculated the distance to your nearest identical copy, approximately 10 to the 10 to the 29th meters away, far beyond even the cosmic horizon. But they're out there, living lives indistinguishable from yours, right down to the quantum state of every particle. This forces us to reconsider fundamental assumptions about identity, causality, and meaning. If infinite copies exist, what makes you uniquely you? Is personal identity defined by physical configuration alone, or does the specific causal history matter? These questions extend beyond physics into philosophy and consciousness studies. Some physicists, like Lee Smolin at the Perimeter Institute, reject eternal inflation precisely because of these implications. Smolin argues that a theory requiring infinite, unobservable universes violates the principle that science should deal with testable predictions. But proponents counter that eternal inflation makes specific, testable predictions about the structure of the cosmic microwave background, predictions that have been confirmed by observations from the Planck satellite and other instruments. The evidence suggests we must accept the philosophical consequences along with the scientific framework. Part B. Future implications. Recent breakthroughs suggest we might be able to detect signatures of the physics beyond our cosmic horizon. The James Webb Space Telescope, launched in 2021, is detecting galaxies from the universe's earliest epochs with unprecedented clarity. Some of these galaxies appear surprisingly mature and massive given their young ages. They shouldn't have had time to form so many stars. This tension might indicate that our models of early universe conditions need revision, but it could also hint at something more profound: influences from beyond the cosmic horizon. If eternal inflation is correct, our bubble universe could have collided with neighboring bubbles shortly after formation. Such collisions would leave distinctive patterns in the cosmic microwave background, circular features or hemispheric asymmetries. Physicists have searched for these signatures. In 2015, a team led by Hiranya Paris at University College London reported potential evidence of 4 collision sites in data from the Planck satellite. The findings remain controversial, with other teams finding no significant signals. But the search continues. Next-generation instruments will push our observational boundaries to their absolute limits. The upcoming Nancy Grace Roman Space Telescope will map the universe's structure with unprecedented precision, potentially detecting subtle distortions caused by horizon physics. The Simons Observatory and CMB-S4 project will map the cosmic microwave background at higher resolution than ever before, searching for the faintest signatures of boundary conditions imposed by the horizon. Perhaps most ambitiously, the proposed Laser Interferometer Space Antenna, or LISA, will detect gravitational waves from the universe's earliest moments. These ripples in space-time itself might carry information from the cosmos beyond our horizon, encoded in subtle patterns that survived the journey to our era. Gravitational waves travel at light speed, but interact very weakly with matter. This means they can carry information from regions that became optically opaque to us, potentially revealing structure beyond the visible horizon. What this means for us, for humanity's long-term future, is profound and unsettling. Our descendants, billions of years hence, will inhabit a universe increasingly isolated from external influence. As galaxies cross the cosmic horizon, the night sky will gradually empty. Eventually, only our local galactic cluster will remain visible, a small cluster of galaxies gravitationally bound to our own, surrounded by eternal darkness. Astrophysicist Greg Laughlin has calculated that in approximately 150 billion years, the observable universe will contain only the galaxies gravitationally bound to our own. Everything else will have receded beyond the horizon. Future civilizations, if they arise, might not discover the expanding universe at all. They'll see only static galaxies, unchanging for billions of years with no evidence of cosmic expansion. They might develop entirely different cosmologies, never knowing the full truth of their situation. Astrophysicist Abraham Loeb suggests we have a cosmological responsibility to preserve current knowledge about the universe's expansion for far future civilizations. Otherwise, they'll be cosmically marooned, unaware of the larger universe that surrounds them beyond their shrinking horizon. The evidence suggests that we live in a privileged moment in cosmic history, late enough for complex structures and life to form, but early enough to observe the expansion and infer the cosmos's true scale. We exist in a brief window when the universe reveals itself. That window is closing. Act 4. The Ultimate Questions. The most profound implications emerge when we consider what the cosmic horizon tells us about the nature of reality itself. Physics is built on the assumption that the universe operates according to consistent laws independent of observation, but the cosmic horizon reveals that reality is fundamentally partitioned into causally disconnected regions. Events beyond the horizon cannot affect us, and we cannot affect them. Do those regions exist in any meaningful sense? This question parallels debates in quantum mechanics about whether unobserved quantum states are real or merely potential. The cosmic horizon extends this question to the largest possible scale. Physicist John Wheeler proposed that observation creates reality through what he called participatory universe theory. If true, then regions beyond our cosmic horizon, forever unobservable, might exist in a fundamentally different state than the reality we experience. The universe beyond the horizon might be quantum potential rather than classical real, solidifying into definite states only when observation becomes possible. What the evidence suggests about reality itself becomes even more unsettling when we examine the mathematics carefully. The equations of general relativity permit solutions where different regions of spacetime have different cosmic horizons. In some solutions, the horizon expands. In others, it contracts. In still others, multiple horizons exist simultaneously. Our universe follows a specific solution, but the mathematics contains infinite possibilities. This raises a question that physics cannot answer. Why our solution rather than others? The anthropic principle offers one response. We observe this particular universe because it's capable of producing observers. Universes with different expansion histories might not form stars, planets, or life. We find ourselves in a universe compatible with our existence by selection bias. But this explanation leaves many physicists unsatisfied. It transforms fundamental physics into cosmic statistics, replacing why questions with why not observations. The most disturbing evidence comes from attempts to calculate the total information content of the observable universe. Using the Bekenstein bound, a fundamental limit on information density, physicists can calculate the maximum information that could theoretically fit within our cosmic horizon. The number is staggeringly large, approximately 122 billion bits. But the actual information content appears much lower. The visible universe contains perhaps 10 to the 80 particles. Even accounting for all quantum states of all particles and fields, we fall short of the theoretical maximum by many orders of magnitude. This suggests either that the universe is extraordinarily simple for its size, or that vast amounts of information